Hey y'all, my goal for this video is for you to optimize your AB, BC calculus exam score. I'd love for you to benefit from my 15 years of teaching and grading the AP exam. If you find this video helpful, I'd love for you to like, subscribe, or leave a comment down below. I'm going to be going over the most essential elements of the AP calculus curriculum, many of which you see on the review sheet on the screen in front of you. This review sheet has all the things you need in order to be successful in the AP exam, distilled down to about 8 pages. If you'd like to purchase a copy for $3, look down in the comment section below to see how to do that. With no further ado, let's get to it. You're going to have to know your derivative rules to have any success on the AP exam. Besides just knowing the power rule, you're going to have to know the product rule. Make sure whenever you have two functions times each other, it's going to be your derivative of the first times the second plus your derivative of the second times the first. It really doesn't matter which order you do them in, as long as you take the derivative of one times the original function of the other when you split it up into, x sine x, for example, two different functions. Your quotient rule, when you're dividing two functions, like in this case, x squared over sine x, we can't combine those or simplify those in any meaningful way. So it's going to be your derivative of the numerator times the denominator minus the derivative of the denominator times the numerator, all divided by that denominator squared. The denominator squared, you're not doing the derivative. It is just the denominator squared. The order does matter because of that negative sign right there. You are going to have to do it in this exact order. Your chain rule, probably the trickiest of them, because College Board is going to put an answer every time for ignoring the chain rule. So you need to make sure you are aware of the chain rule. Anytime you have a function that is embedded or inside of another function, like in this case, the x squared is inside that sine x, we're going to take the derivative of the outer function with the inside function unchanged. That is a big key. That inside function remains unchanged. So you take the derivative of sine, which is cosine of x squared, but then times the derivative of that inside function, which is going to be 2x. You could have this in this case, down here, the College Board favorite, where they like to have three chain rules kind of embedded inside of it. There are three chains. So you have to kind of recognize that sine to the fourth power is really this outside function right here, and it can be rewritten this way. I would encourage you to rewrite it this way so you can kind of see all three layers of functions. And so you have to take the derivative of the outer function using your power rules. That's why we have 4 sine x squared to the third. Recognize that inside function does not change, times the derivative of the inside function. So this is almost as if we have already taken the derivative of this, and now we're just going to take the derivative of that inside function only, like we did in the previous problem. And so it's just going to end up being cosine of x squared times 2x, like we saw earlier, okay? And so in this case, we'd have 3 layers of that, and College Board really loves on multiple choice to give you a question like that. You're going to have to know your natural log derivative, and so the rule for that is 1 over the argument of natural log. It is not 1 over natural log of u, and then this du dx, that is the chain rule. So we're going to just use the natural log rule for this example of natural log of x squared plus 5. We say 1 over x squared plus 5, but then times the derivative of that inside function, which is just going to be 2x. Your exponential base e derivatives. We love e because it has a very simple derivative. Your e to the u, which in this case u is some sort of function of x. It's just going to be rewrite it. That's your rule. It's itself. But then you have to deal with the chain rule. So du dx is the derivative of that exponent. Okay, and that is going to be the chain rule. So if we have e to the x squared plus 5, we just rewrite that e to the x squared plus 5 times the derivative of the inside function. The derivative of the inside function is just 2x, and that is your derivative. I like to include the second fundamental theorem in with my derivative rules because at the end of the day, it is a derivative rule. We're taking the derivative of an integral defined function. We're taking the derivative of this integral right here. Realize your antiderivative and derivative are going to cancel each other out, just like multiplication, division, addition, subtraction, same thing. So our derivative, if we were going to find the derivative of this integral from 3 to x of t to the 5th sine t squared, it's just going to be x to the 5th sine of x squared, right? So realize the t is a dummy variable, the actual variable is that x, and it is just going to get plugged in after you take the antiderivative, but then the derivative reverses it right back. the same thing, when we have the chain rule, we have to realize the chain rule, the inside function on this second fundamental theorem derivative rule is just in the bound. So it is just the g squared. So whenever you see this, and this x squared replaces the t, and we get this x to the sixth on the inside, notice the derivative of the inside function is only the derivative of the bound. It is not going to end up being 6x to the fifth in this derivative rule. The other derivatives, you're going to have to know these three for sure. They come up a lot for sine, cosine, and tangent. Whether you have a lot of time to study your derivatives or not, I would focus on those three. 90% of your derivatives are going to be sine, cosine, and tangent. And you maybe every 3 or 4 or 5 years, you're going to have a secant, cotangent, or secant. So I wouldn't study them as much. Make sure you know the sine, cosine, and tangent. Same with the arc trig derivatives. College Board's not really trying to test you on your memorization skills, so they don't really put them on very often. For the arc trig derivatives. If you have time, you can do them. I did put the arc trig derivatives in my review sheet that you can get at the bottom of the page. F prime, F double prime relations are all over the multiple choice of the AP exam. You are going to have to know these down cold. You have to know that f prime is the slope of the tangent line of f, and f double prime is the slope of the tangent line of f prime. Often you're going to be given an f prime graph, and you're going to have to be able to know information about f double prime, so you have to look at the slope of that f prime graph to tell you the signs of f double prime. Some things to know. You need to know what a critical point is. They use that. That's basically where the maxes and mins could possibly occur. Doesn't mean they have to. It's where f prime equals 0 or is undefined, but not the endpoints. Endpoints can be maxes or mins, but they are not considered critical points. Maximums and minimums, they're going to occur where f prime equals 0, f prime is undefined, and you will see that a maximum will occur where f prime changes from positive to negative. That means a function went and had a positive slope and then a negative slope, and that's going to create a maximum. A minimum is going to occur where f prime changes from negative slope to positive slope. These are not ideas that you cannot you have to know. They are not beyond anybody. You don't have to memorize these. You need to make sure you understand those ideas. Points of inflection are where a concavity changes on a graph of f. But the way we look at this, we're going to be looking at f double prime, because f double prime tells you the concavity of the f graph. So we want to go ahead and see where f double prime changes signs, not just where f double prime equals 0. College Board loves to test your idea. If you know that it is not where f double prime equals 0, it is actually the sign change that is important, because that signifies the change in actual concavity of the f graph. F is increasing when f prime is positive. That is a big idea. If you're ever asked to analyze what a derivative means, you're looking for what the derivative is, positive or negative, to determine whether or not f of x is increasing or decreasing. The second derivative is going to tell you the concavity. So if f double prime is positive, f of x is concave up. But imagine if f double prime is positive, that means that f prime is increasing. So if we're given the f prime graph, you look where f prime is increasing. That's going to tell you where f is concave up. Same thing with concave down. F double prime is negative, or f prime is decreasing. Now, the biggest thing, the most important thing you have to know, and if you want to have any success on the AP exam, is the fundamental theorem, and really understanding this relationship right here and what it means. And so I think this statement that I have right here written below is the most important thing in all of calculus. And it's this idea here. It says, when f prime is positive from a to b, f of x is increasing from a to b. Now, the area underneath that f prime graph from a to b is the amount that f of x increases from a to b. That is what the fundamental theorem of calculus is saying, right? It's basically saying that this area underneath f prime, that is what that integral means. It finds that, computes that area, and is equal to f of b minus f of a, which is really just the change in f of x. So you have to really make sure you understand that idea. So in this example down here, we're looking at, again, when f prime is positive from a to b, f of x is increasing. And this is also vice versa. If f prime is negative, also decreasing, and the amount it decreases would be that area. So for example, if we're going to go from -5 to -2, you have to recognize that f prime is positive on that entire interval. So that means that f of x was increasing, and the amount increases this area. This area is 5, so we know that from if I had a value of f of -5, let's say equals 10, then I know that f of -2 is going to equal 15 because f prime was increasing on that interval by whatever that area is. Same thing, likewise, if we're going to go ahead and say when f prime is decreasing, when f prime is negative, f of x is decreasing. And so the amount it decreases is equal to this area. So this area is going to end up being 7. And we say this is below the x-axis. We're going to say it is -7. So we're going to end up talking about f of, if we want to find out what f of 3 is, well, the value decreased by 7 units. So we know f of 3 would be at 8. So it's a quick, easy way to do the fundamental theorem, just kind of intuitively from this statement right here. 100% you're going to be given a graphical analysis question where you're going to be given some sort of derivative graph. Now, it may be disguised, but you're going to be given a derivative graph, and they usually put it in 2 different ways. One way is they give you an f graph, but then they give you this integral defined function where what we have to make the connection immediately is that g prime of x equals f of x. And so what that means is that this f of x graph is really your g prime graph. And then you can go through and answer all these questions where it's asking you questions about g. Is g increasing? What is all these g prime, g double prime? What values where there's a point of inflection for g? And absolute maximums are g. But really all they've done is they've disguised this question and they're giving you a g prime graph to answer a bunch of questions. The other way they ask you this question is they give you f prime and then they give you a point, in which case you can use the fundamental theorem to find other values of f. But again, these questions are very similar. You have to be able to analyze and understand how to analyze these f prime graphs. If you're interested in this question I have right here, it is in the review sheet down in the comments section. So along with knowing your derivative rules, you're going to have to know all the integration rules as well. This is your other operation of calculus that you have to know. And so a couple properties you have to know. If we ever have a situation where you have the lower number in the upper bound, you're going to want to switch that and make it the opposite. And that way it helps you whenever you're doing those graphical analysis questions. It'll allow you to go from lower to higher values. It'll allow for your dx to be positive, which is going to make values above the x-axis positive, areas below negative, which is what we like. So we usually like to switch it to have a lower number in the lower bound, upper number in the upper bound, and that's how you can change that. If you ever have an integral where you have the same lower and upper bound values, then that integral will equal 0. You're going to have to know your derivatives of your trig functions. They're going to be the opposite of the integrals are going to be the opposite of your derivative values. The tangent one doesn't show up too much, but it's good to know instead of having to derive it from, sine x over cosine x and using a u substitution. It might be worth your while to know that one. Again, e to the x is just going to be e to the x. It's just the same as the derivative. Derivative of e to the x is e to the x. Antiderivative of e to the x, e to the x. Your special one, when you have 1 over x, this one shows up a lot. It is going to be your natural log of the absolute value of x. You need the absolute value so that the domains match up. Realize you cannot use a natural log antiderivative whenever you are trying to come up with 1 over x squared or 1 over anything besides a linear function. So you have to change this to a negative exponent and then do your antiderivative power rule, which tells us we need to go up 1 power and then multiply by the reciprocal of that new power. So for example, in this case, we're going to take the antiderivative of 3x to the 6th, we go up 1 power to x to the 7th, we multiply by 1/7 and then times 3. Now, one thing College Board likes to do, you're going to have to deal with inside functions. Now, there is a whole u substitution process that I'm going to describe down here. You can see in my review sheet down in the comments section, but 80% of the u substitutions are going to fall into this simple u sub category where the inside function is a linear function. And so we end up saying the antiderivative e to the 5x, we need to be able to do these in our head because the AP test, if anything, it is a speed test and you need to save time. You do not need to be doing the whole u substitution process. So we're going to go ahead and And just remember, whenever you take the derivative of e to the 5x, it's e to the 5x times 5. When you do the antiderivative, instead of multiplying times 5, you're really just going to divide by times 5. And dividing is the same as multiplying by the reciprocal. And so that's why it's going to end up being 1/5 e to the 5x. If we see this 1 over 3x plus 2 right here, we have to recognize that's a natural log antiderivative. And the derivative of the inside function is 3. So we're going to multiply by 1/3. Same thing over here. This is a sneaky one. Sometimes students don't see that there's an inside function, that your x has a derivative of -1, which is going to give you that negative. They really love to do this one on solving those differential equations. They've done that a few times. Okay, and you can see the same thing over here. The antiderivative of sine of x is going to end up being negative cosine of x, but we have a derivative of the inside function that's going to be 2 pi over 3, so we need to multiply by 3 pi over 3 over 2 pi. So U substitution, it's just a way of reversing the chain rule. And so oftentimes you're going to end up having an inside function inside of something you're trying to integrate. So in this case, we see that this x cubed is our inside function. So we're going to make u equal x cubed plus 1. And then we take the derivative of that. And our derivative du dx is just 3x squared. And at that point, you're going to solve for dx by multiplying both sides by dx, dividing by 1 over 3x squared. And we end up getting what dx equals. At this point, we should be able to substitute our u back into our original integral and substitute in dx. And when we do that, and if we've done it correctly, and it is a u substitution integration problem, the x squared should cancel. We should be just left with u's. Now, don't forget that this 3 right here, and so I like to pull it out and make it a coefficient, so 1/3. Notice also the bounds have changed, right? Because in this original integration, this goes from x equals 0 to x equals 2. So we need to actually find the corresponding u values. You do that by plugging it into this your u equals equation. So when when x equals 2, your u is going to equal 9. When you plug in 0, 0 plus 1 is going to equal 1. So when x equals 0, u equals 1. Now we have an integral right here that is simpler. We can just evaluate that integral. We never have to go back to x's. So we can just do our regular antiderivative, plug in your upper bound minus lower bound, and get this value. Now, if it was a free response question, you could just leave your answer like there. There's no points for simplifying on the AP exam. Now, if there were not bounds, you would have to plug your x back in for u in the last step. And so your integration would look like this. Now, 2 of your free response questions on the AP test are going to involve rate functions, whether it's a rate in, rate out function, or just some sort of analyzing a rate function. And it's going to end up, and you'll have a Riemann sum question, which is typically some sort of rate function in a table. And you're going to have to be able to use a Riemann sum, because a Riemann sum is generally just a way to evaluate an integral or approximate an integral value. Now, an integral is used to accumulate an amount of a variable rate. And so that's why calculus is so powerful, is we can take rates that are changing and we can actually multiply rate times time. We don't have to, like algebra, have to have a constant rate there. We can break it down into smaller and smaller pieces and actually multiply that rate times time at every instant of time on some interval. So for example, if we have W of t, which is the rate by water flows into a tank in gallons per hour, we can find this integral where we multiply our gallons per hour times hours at every instant of time from 0 to 8, and that'll find the amount of gallons that flowed into the tank from 0 to 8. And you can see you could always find the units of an integral by just looking at what are those different values. So this is my W of t units multiplied by my dt units. If we do that, these units cancel right here and we end up getting units of gallons. And so dt just has units of time, so realize that that is just a time unit. A Riemann sum is just a way to approximate an integral by using rectangles in order to find the area underneath the curve. So typically we're just going to be able to take, our height is going to be f of x times the width, which would be dx. And so we're going to use, a certain number of subintervals in order to find the area under the curve. Now, if we were going to find an exact integral, realize that is basically a Riemann sum, but we're using an infinite number of subintervals of infinitely thin width. Okay. Now, on a Riemann sum question, we're going to be given a table of values, and we're going to have to be able to approximate the area under that function, under using either left, right, midpoint, or trapezoidal sum. But realize it's the same principles we talked about earlier as an integral as an accumulator, right? And so, for example, if we're doing a left Riemann sum, use the value on the left-hand side of the subinterval as your rate or your value that you're going to multiply times dx, in this case, or delta x. And so, for example, this third rectangle on this subinterval from 6 to 11, it's a 5-hour subinterval, but we're taking the value on the left-hand side, which is going to be at 6. So we say 17 gallons per hour for 5 hours. And so that subinterval, that third rectangle, it represents 85 gallons that flowed into the pool or whatever we're talking about. If we're going to do a right Riemann sum, same thing, we're just using the value on the right-hand side of each subinterval. That's why I'm going 3 times 12, 17 times 3, and then 20 times 5, right? And then 22 times 5. Now, a midpoint Riemann sum, the table is going to have to be set up in a particular way for us to be able to use that. And so you have to realize we're going to use a subinterval from 0 to 6, but we use the value at the midpoint. So in this case, you could only have 2 subintervals here in order to do this, right? Now, a trapezoidal sum, it's really just essentially the left and the right Riemann sum averaged together, because we're taking the average of our left and right. And that's really what's shown right here, is I'm taking that 10 plus 12 and I'm dividing by 2 and I'm finding the average of that rate and then multiplying it by that subinterval of 3. And so we do that and the same thing's happening, right? We're finding that average flow rate in gallons per hour times 3 hours. And so that's what each rectangle is still going to end up being, that same thing as what the integral value equals, which is that rate times time, and that a number of gallons that flowed into a tank or a reactor or whatever we're talking about. While solving differential equations is not the biggest topic on the AP exam, it is the single highest valued question on the AP exam. On a free response question, it's worth 5 points. And when the difference between a 3 and a 4 is about 9 to 10 points, getting this differential equation question is going to be very important. And from my experience in grading, I see students that get 4 or 5 out of 5 on these, or 0. And so it's a high stakes question, and making sure you understand what the question is asking, because really at the end of the day, it might be the easiest 4 or 5 points on the AP exam, but a lot of students zero out on it and a lot of students get 3 or 4. And what I found with my class, years that students do really well are years that the students do best on the differential equation question. So making sure you recognize, first off, when you see a differential equation that looks like this, you've got to think to yourself, at some point we're going to have to do the separation of variables and solve. And so that's really it. You have to make sure you know how to separate the variables. You need to get the y's with dy, the x's with dx. Now your dx and dy need to be in the numerator. You've never seen an integral where it was y divided by dy. It's never happened. So it's got to be, we have to multiply. In this case, we're going to have to multiply by 1 over y squared on both sides and get, 1 over y squared dy equals x dx. Now, sometimes it throws students off whenever the question's not in x and y, it's just in b and t. And we're going to have to do the same thing. We're going to have to separate our variables. So I've worked this example, and I kind of show this example. This is the same example that's in my review sheet in the comment section. So we're going to go ahead and multiply by 1 over b squared to each side. And then we're going to multiply by dt onto each side. We separate the variables. If you can't do this algebra step, you're going to end up getting 0 out of 5 on this, and it's going to be catastrophic. So make sure you understand how to do the algebra steps to separate the variable. It is not just moving the b squared to the other side. You need to multiply by 1 over b squared. Now we integrate both sides. These are simple integrals. Now the thing is, you cannot use a natural log to integrate this. You have to change this to b to the negative second. And if you do b to the negative second, go up 1 power, b to the negative first times negative 1, and you end up with negative 1 over b. The right side integrates fairly simply with t to the t squared times 1/2. Now at this point, what we want to do is we want to take our initial condition and plug it in. If you do that, if you just get to this step right here, you've already earned 4 of the 5 points. Okay, so really it's a pretty simple way to get 4 4 points, you just have to make sure you understand the question. You'll see things like use separation of variables to solve for b of t. Or you'll see something asking you for find the particular solution, y equals f of x. Realize you're just trying to find the antiderivative of these two functions up here. And then the last step is once you solve for c, it's just a matter of plugging in that value in for c and then solving your equation for b to get the final point. Typically, you'll be given a free response question that'll be over area and volume. Realize all the volumes have the same idea. It is the area of some cross-section times dx, right? So if you have some area and you give it a little bit of thickness, now you have a volume. This integral accumulates all of those little slices of volume and adds them up to create the entire volume. Realize you're going to have to be comfortable doing these volumes in dx and in dy. Okay, and I'll kind of show you how that's going to work a little bit later. The disk method. So this is if your cross sections are a solid disk, and the cross sections are going to be a circle, which is pi r squared. So our volume is just going to end up being pi r squared integrated over whatever interval we're talking about. The washer method, this is the same thing. It's just going to be a big circle minus a little circle, right? I mean, you have a big circle. The cross section would look like this, but we're finding this area in between of each cross section. And so in this case, we're going to have a big radius squared minus a little radius squared. Basically, pi r squared minus pi r squared. Big circle minus little circle integrated over some sort of interval. You might have a square cross section, which the area of a square is just L squared. And so that length is typically bounded by two functions. So it's typically going to be the top function minus the bottom function. So again, that area of that square is going to be integrated over some sort of interval. You might also have a rectangular cross section, which again would be that length, that same length we just talked about in the square, but this time it'll define a particular height. And so you'll have that same integral, which is going to be the L of x function times the h of x function. But remember, don't square that L in this case. All right, so now in this problem right here, it says find the volume of C when this region C is revolved around the x-axis. I always like to start at the axis of symmetry, the axis of rotation, which in this case is going to be the x-axis. So I start right here. I draw the radius up to the edge of the boundary that I'm going to be rotating. That is my r. And realize we have this pi r squared. And so to find this length r, it is just top function minus bottom function. So it's going to be 2x minus 0. In this case, it's going to be 2x minus 0, which is really just 2x. So that's why I have, pi 2x squared dx. If you're asked to rotate this, rotate around region B around y equals 8, again, I'm going to start at the axis of rotation, and I'm going to draw a radius to my outer boundary. I'm going to draw a radius to my inner boundary, right? So my big radius, I have my big R, and I have my little r right there. And so if I want to find those lengths, because that's going to be plugged into my cross section, which is pi big radius squared minus little radius squared. So I really need to find out what each of those are. Well, to find this length right here, it is going to be top minus bottom. So big R is just going to be 8 minus this function 2x. And then my little r is going to be 8 minus 4 square root of x. And so I can see that's really what we've done. We've just taken those values and plugged them in. Here's my big R, there's my little r, and I plug it into that formula. Be aware whenever you're going to find something rotated around the y-axis. Well, in this case, I'm going to, again, start from my axis of rotation, and I'm talking about region A. So I'm going to draw a line to my outer boundary right there. So there's my radius. The issue here now is that the thickness of my radius I drew is now in the y direction. So that makes it a dy integral. Okay, and so we need to find that length. And so everything in a dy integral is going to inform everything we do. The bounds are going to have to be from y equals to y equals. That's why I'm going from y equals 0 to y equals 8. I need to change my radius in terms of y. So I have to rearrange this function over here and just solve. So I have this y over 4 equals square root of x. I square both sides, and so I'm going to get y squared over 16 equals x. And so that's where my radius comes in. It's going to be that square root of, y squared over 16 minus 0 is that length right there. And so that's what I'm going to use whenever I do my pi r squared. The same thing can be done for the washer in the y direction. Now, if you're going to have a square cross section, it says B is the base of a solid with square cross-section perpendicular to the x-axis. Okay, so I have region B here, and I have cross-section perpendicular to the x-axis, so that's going to be this length right here. You have to imagine that this length right there is also sticking straight out of the page, and so it's going to create a square cross-section, and so we need to find this length. That length is found by top minus bottom, so that length right there is really this 4 square root of x minus 2x. And so that's where we're getting that length. This is just L squared dx, because this is, again, just the area of that cross-section that's being determined. Now, when you're doing a rectangular cross-section, notice it was just that same L, but then times whatever the height that was defined for the problem. So recall, your derivative is the slope of the tangent line. It is a slope, and it is a slope from 2 points as those points get infinitely close together. That is what this limit definition of a derivative is saying. It's finding the slope as that x value, which is h, that delta x, so that change in x is approaching 0. That's what that h is in there. And so when you see this limit, I have yet to see a multiple choice section of the AP exam that does not have at least one limit definition of a derivative on there, if not both of these. And so you have to realize that in this example, this question right here, if it asks you for this limit right here, it's really asking you to find the derivative of sine of x, which is going to be cosine of x. Or you might see something here that looks like a slope right here. y2 minus y1, y2 minus y1 over x2 minus x1. That's really happening as the 2 points, as the two x values get really close to each other. That is a derivative. So really what's asking you to find is the derivative of sine of x at 5. Well, the derivative of sine of x is just cosine of x, and then we plug in 5. And so we end up getting this cosine of 5. Limits. So being able to find a graphical limit is going to be important. Just remember the key thing here is you must approach the same value from both sides. So for example, at 2, from the left and from the right, we are approaching a y value of 1. So this limit would equal 1. At 4, 1, 2, 3, 4, notice from the right, we're approaching 5. From the left, we're approaching 1. So they're not approaching the same value. So this limit does not exist. There you go, Lindsay Lohan. From x equals 1, it doesn't matter. Sometimes students get confused whenever there's not a circle, there's not a dot there. But realize we're approaching the same value from both sides. We're going to go ahead and get -2. Sometimes you'll have a one-sided limit as x approaches 0 from the positive. You're going to end up getting, just as you come from the right-hand side, this is the positive side of the graph. So you're coming from the right to 0. And so that would end up being -3. Over here, when we're going from -4, 1, 2, 3, 4 right here, notice that value doesn't exist. It does not matter. A limit, we do not care what is right at -4. What we care only about is what value are we approaching. We are approaching 2. So this is going to end up having a value of 2. Now, when we're talking about f of a value, that's actually what happens at that value. So a limit, we don't really care. We only care about what we're approaching. When we say like f of 4, we're going to get 2, because that is the value right here of the function is actually at 2. At -2, we're going to take where the solid dot is. So that's going to be -2 right there at that value. When we talk about -4, there's no value right there. So f of -4 is undefined. We do not have a value for that. Now, when we're talking about an equation and you're asked to find the limit, we're pretty much going to just use L'Hopital's rule. And so typically on these limit questions, when you plug in the limit, you're going to get 0 over 0 or infinity over infinity. That's typically what's going to happen. If you don't get 0 over 0 or infinity over infinity, then just write that number down. If you ever get like 5 divided by 0, then that limit doesn't exist because that's division by 0, right? But if you get an indeterminate form, which is going to end up being either 0 over 0 or infinity over infinity, what you're going to need to do is use L'Hopital's rule. And what L'Hopital's rule says you can do is you can go ahead and take the derivative of the numerator and the denominator and then apply that limit, right? But this can only be used if you get 0 over 0. So you're going to have to show on your FRQ that you checked to make sure that the derivative of the numerator and denominator were both 0. So if you have a question like this where you're asked to find the limit as x approaches 0 of sine of x over 4x, you must show sine of 0 equals 0. F of 4 times 0 equals 0. And so therefore, then you want to go ahead and write out this limit. You want to take the derivative of the numerator, derivative of the denominator, and then plug in the limit and get 1/4. What you do not want to do is at the beginning of this problem say, oh, this equals 0 over 0, because it doesn't equal 0 over 0. It equals 1/4. You saying it equals 0 over 0 is going to lose you a point, because they're going to say, you just said that this limit was undefined, which is not true. The limit actually equals 1/4, right? So here's your L'Hopital's rule down here. If you produce an indeterminate form, and only if it produces an indeterminate form, so if you don't get an indeterminate form, you cannot use L'Hopital's rule. It's basically saying that your your limit as x approaches c of f of x over g of x is going to equal the limit as x approaches c of f prime of x over g of x. Sometimes you're going to be given some sort of known relationship between two quantities, and you're going to be asked to find the rate at which those known quantities are changing with respect to each other. In this case, it's a related rate question. So typically you'll be given some sort of relationship, like say here, and then you'll be asked to take the derivative. Now you take the derivative just like normal, but remember, every single variable is going to have its own chain rule and its derivative with respect to time. So for example, p squared is going to be 2p times dp dt. And your 1/4 h, it's going to be very tempting to say the derivative of 1/4 h is just 1/4, but really it's 1/4 dh dt. And same thing with 2h cubed, it's going to end up being 6h squared, just like you normally would take the derivative, but then times the derivative of the inside function. The derivative of h is dh dt. Now, typically these questions, what they're going to do is they're going to give you enough information in the problem to plug into your derivative, and they'll be asking you for one of these variables, one of these unknowns is typically what's going to happen. And so you just solve for the one unknown. This is very similar to what you're doing with implicit differentiation, right? Where we're taking the derivative with respect to x. So when we take the derivative of x squared, we don't need a chain rule for that, because the derivative of x is just 1, or dx dx, dx over dx. It's the same thing. But the derivative of y is dy dx. So when we take the derivative of negative 3y squared, it's going to be negative 15y to the 4th times the derivative of the inside function dy dx. So that's really your chain rule is what's happening. Now, in implicit differentiation, you're going to need to solve for dy dx. So after you take the derivative, then you're going to have to be able to solve and isolate dy dx to end up finding your derivative. Thanks for watching this video. I hope you found it useful. If you like what you saw here, please like, subscribe, or leave a comment down below. Again, if you want to purchase this review sheet that I went over, you can do that. Look down in the comments section to find out how you can do that for $3. Thanks so much. Good luck on the AP exam.